Good afternoon to everyone on Zoom. You can just give me a thumbs up that you can hear me well. That'd be appreciated. Thank you, Landon. Thank you, guys. We're gonna start here in a minute. Okay, we can go ahead and begin. Good afternoon to everyone in class here as well. So let's speak a little bit about course logistics, and then we will dive into our lecture. So, where are we at currently in the modules? We're still in week 8. So, this week we have already discussed TCP itself as a protocol, and we will talk about congestion control, the principles of congestion control, and the next lecture will be TCP itself. So today's lecture will be kind of short and compared to the one on Monday, because Monday is going to be a whole lecture about congestion control regarding TCP. So that is where we're looking so far, and then we're looking to discuss TCP congestion on Monday of next week, and then Wednesday is going to be no class. That is the time for you to review the material, and then our midterm is going to be on the 20th. How is the midterms for you guys for your other classes? Is it around the same timeline or?
Mine was this week.
Oh, yours is this weekend? Okay. Is it good to have it on a weekend? No? Okay. Yeah. But it must be online, right?
No.
It's not online?
Mine.
Oh my God, that's ridiculous.
Less than an hour.
That's a lot. Okay, so just a brief touch up on the last lecture. So, because before we talk about congestion control in terms of the principles of it, it is kind of connected with flow control as well. So we wanted to touch up a little bit on that. So far in the roadmap, we have discussed everything so far till TCP congestion control and principles of congestion control. So we talked about the go back and N as a mechanism. We talked about the selective repeat, and we talked about TCP as a protocol itself. We talked about the structure, the acknowledgements, the sequence numbers, how they work together hand to hand. We talked about how do they calculate the runtime trip and the timeout for each packet for it to be resent. And we talked about, this is kind of important that I wanted to touch up on, is the TCP fast retransmit, because this will be included in our congestion control protocol or principles. So we said that the TCP fast retransmit is basically if the receiver receives 3 or more or 3 or additional acknowledgements for the same data or for the same packet that was sent, or the same acknowledgement, already kind of knows as a way of detection that the packet needs to be resent. So it does not wait for the timeout error or the time that we have set in place for it to be resent. So this is something to remind you because we will talk about it more today. We talked about flow control. How can we make sure the receiver does not get overflood, or the buffer of the receiver does not get overflood with data, such that it can have a buffer that flows well where the data in the buffer gets transported to the application, and the data that is coming from the server or the other host is stored in the buffer and has enough storage for that. And we talked about the idea of flow control. This is basically what it is. And we talked in a human analogy where here, or the dog or the kid is trying to drink water. The flow of the water is very fast. They cannot drink water in a matter in a matter where they can drink water in comparison to the data. If the buffer is being overflowed with data, it cannot have space for everything. So we must have a way to control that, to tell the sender, hey, this is how much storage I have. You should control how much you send. And this is the way we dealt with flow control. And basically, this is the idea. We're going to have a free buffer space and a buffer data. And the buffer data is going to go up to the application. The free buffer space is what we have. So that is for us to communicate with the sender. The receive window in terms of the TCP segment format is the indicator that tells us, hey, how many bytes are we willing to accept from the receiver side. And then we talked about connection management. This is about the handshake. And we highlighted why the two-way handshake is not ideal for us and what are the common mistakes from that and how we transferred into a three-way handshake interstate. And that is what currently TCP is using. This is another human way of analogy of that with rock climbing. And that is that. So we wrapped up last lecture. For today's lecture, let's go ahead and begin that one. Yeah, let's go ahead and start. So as usual, the lecture is recorded and some of the slides are being borrowed from the book. And there's a direct link to that. So for the roadmap, we have wrapped up TCP, the connection of TCP and the principles of TCP as a data transfer protocol. We have spoke about UDP. We talked about multiplexing and demultiplexing. We talked about the transport layer as a service. So next, we will talk about principles of congestion control. So we want to start looking at the basic question of what do we mean exactly by congestion? The word is there and it is formalized in networking, and we need to define it and see how it happens and how we can deal with it. So this is part of the objective of this lecture. So congestion happens when there's too many sources send too much data too fast for the network to handle. And we know that each host and each client has a transmission rate, and their rate handles an amount of bits over seconds. So when the incoming packets rate exceed that rate, the queue begins to line up. And as the load increases, delays get larger and larger, and eventually the buffer will be overflown. And that leads to packets dropped or lost. And we discussed that in chapter 1. So the congestion shows up as long delays and packet loss in the network. There is an important distinction that I want to make when we speak about flow control and congestion control. So they're not ideally the same. Congestion control is like many senders are sending too much data or too fast for the network to handle. Flow control is one sender sending too fast for the receiver. And we spoke about flow control as a problem itself and how we can deal with it. And one of the ways to deal with it is by telling the sender, this is the window size that I can receive for me to process. So we just want to make sure those terminologies are clear before we go ahead and look at the difference. So next, what we're going to look at is what are the causes of cost congestion, and we'll talk about a scenario based. So just to connect back and more on congestion, what happens during congestion is that we know that when packets are lost due to congestion, the sender will retransmit them. And for us to retransmit these packets, we have multiple ways. We said in the TCP fast retransmission, if we receive multiple acknowledgements, like more than 3, that is one sign or indication for us to resend. Also, if the timer runs out that we have set, this is another indicator for us to resend the data, or we receive a negative acknowledgement. This is also another indicator. So for retransmission, it does not really treat the symptom. What it does, it just retransmits the data. So it is not the solution for the actual cause. And the real cause is that we are many resources trying to build or send data fast. So the retransmission, yes, it deals with packet loss or packets that were dropped or they were corrupted or congested, but it even adds more traffic. So we need a way for us to control the sending rate so it becomes critical in avoiding network overload. So let's start building this first scenario step by step. And always the first scenario that we discuss is the state of art in terms of like everything is perfect, but that is usually not the case. So here we have a simple setup. We have 2 hosts and we have 2 servers, host A and host B. And we know that each of the host has a transmission rate, and that is defined by each host. And then we also have a buffer that buffers or stores the packets or the data that is being sent. And here in the assumption that we have in scenario 1 is that we have an infinite buffer. So that is purely theoretical, but it helps us reason for us to reason clearly. So that is not realistic in terms of when it comes to the idea of the buffers that we have or the router buffer. So both input and output link capabilities are R bits per second, and we have 2 flows here in this specific image. We have flow from A and we have flow from B. So let's take a look at that. Flow 1 is going, we have the red flow and we have a blue flow. And the blue is kind of joining host A, and they both share the same output link. So now for us, we want to label the red flow states. So on the sender side, we have lambda n. This is basically an indicator for the original data. This is the payload data that we're dealing from the application. On the receiver side, we have lambda out. This is the throughput. Basically, our input is going to be the data. Our output or throughput is the data being received on the other end. So because there are buffers and we have in this scenario infinite buffers, there are no packets lost. So whatever we send as lambda in will be lambda out, and every packet will go eventually and come out. There's no loss, just waiting. So that is the idea that we have here. But a key question to highlight here is that what happens when the AN increases and gets closer to R/2? So the total output capacity of the router is R. And since there are 2 flows that we are sharing from host A and B, each one gets R/2. So if both send at the same rate, R2 here represents the maximum per flow throughput, so possible in the shared link scenario. So if both of them are using this link and it's shared, and they are both sending at the fastest rate that they have, we will have some sort of result. So the first result that we see here in the plot, it shows a linear scale or a linear increase until lambda n reaches R2. Then it flattens. So you really can't go any higher than the transmission rate that you have that is assigned per host. But what could happen is that here, the second plot that we have, we notice that the delay grows exponentially or sharply as AN approaches R2. That's because packets are queuing up. So the link is getting saturated. So even in this idealized setup that we have, where we have no losses, congestion itself introduces a cost. And the cost that we have here is going to be delay. So delay will happen, and we will see how we deal with that. So next, we'll see what changes we remove. We remove the infinite buffer assumption that we have in scenario 1, and we'll see what changes happen. So if for every scenario, I try to add an analogy outside of the idea that we discussed to just give you, for it to be more understanding. So for this scenario 1, we have two people sharing one line or sharing one phone line, and the line can only handle one voice at a time. So it is half duplex in the idea. So like a link with the capacity R. If both of them start talking faster, then their words queue up, waiting to be sent. So each person effectively gets half of the line capacity, so R over two. So nothing is lost, but the waiting time will grow, just like the delay we saw with lambda n as it approached the R over two, or the transmission rate for the two hosts. So even without packet loss, I want you to understand that delay is still going to be existing. So the network is going to be simply busy. So we're going to use the same setup that we have. We have two hosts, two servers, two flows. But what happened here is that the buffer for us is not is finite, so it's shared output link of the buffers. So, and we know that we have a certain buffer. When the buffer fills up from the packets that are arriving, if the buffer is filled, then the packets will be dropped. So from reliable data transfer, we remember that when packets are lost or timed out, the sender will obviously retransmit them. And this is an ideal or already a set mechanism that we have. So that means the sending rate now includes both new data and retransmitted packets. Why do we include retransmitted packets? Is because we have loss here due to the buffer. So we want to define these clearly here. We want to define the data that we have. So lambda n is still going to be the original data from the application. This is similar to scenario one. Lambda prime n is going to be the total rate of data that is sent by the transport layer. So that includes the retransmitted data. So the router packets are arriving at lambda prime n, not lambda n. So that is the difference. So when we send data at the first phase, we are sending lambda n, which is the original data. But to do for various reasons, if the packets get dropped or our set timer for this specific packet runs out, then it would send lambda prime n. That is the retransmitted data. And the application still sees a lambda in. It does not see the lambda out because we have every piece of data that is being delivered, it is counted as once. So if the data gets retransmitted, it will neglect the second retransmitted data at the delivery phase. So the transport layer sends lambda in and lambda prime because it includes retransmission. But for the receiver, it will only include one source of data. So it will diminish or neglect the retransmitted data. So it will not be a duplication. So the idea that I want to deliver here is that, in short, retransmission also adds an extra load to an already congested link. So it makes the congestion even worse. So that is also one thing that we have to keep in mind when it comes to the idea of congestion. So you're still building up on the same scenario. We want to see the causes or cost of congestion. So this time, let's imagine an idealized world where the sender has a perfect knowledge of the router buffer space. So like it knows exactly there's room to send a packet. And I have some transitions here that should highlight the idea. So we see that the host is sending the data. And at the transport layer, we take a copy of the data. Why do we take a copy? It's for retransmission. And every packet is gonna be sent, obviously. So here, I think if we repeat the retransmission here, it gets sent perfectly, right? It's not gonna be congested or dropped. Yeah, there's free buffer space. This is a scenario. It gets stored and then it gets sent out. So there is no retransmission here or no wasted capacity. So the throughput still follows the same pattern as scenario one. We have lambda in for the input and lambda out for the outputs. So the only issue here in this scenario or this phase of scenario two is that we have the same problem, which is the delay, which grows as larger inputted data approaches the maximum length that we have, just like we saw in scenario one. So even with perfect control, no losses, congestion still causes queuing delays. Here, same scenario we're looking at a different perspective. So we're gonna kind of relax on the assumption of perfect knowledge. So this time the sender only has a partial awareness of what's happening in the network. So same data is getting sent. We take a copy of it. It goes to the buffer. There's no buffer space. The packet is getting dropped. So meaning that the packets can be lost when they reach the router if the buffer is full. So the sender itself does not know when a packet has been dropped. Only we will retransmit if it's sure that the packet was lost. So this means fewer unnecessary transmissions than before, but still some packets are getting discarded at the router. So the throughput now depends not just on the sending rate, but also on how often the sender needs to resend the lost data. So even with smarter behavior, congestion still costs us in terms of delay and occasional losses. So we also have to deal with the buffer as well. We do have a buffer for a reason, but we must control it in a way that is ideal for us. Now we're going to extend, okay. We're going to extend the scenario a bit further. So let me just go back a little bit. And here we have the buffer is perfect. Okay. Okay. So we know the packet is going to be dropped when the buffer is full. The sender retransmits it once it detects the loss. So the retransmitted copy might later find. So after we drop the packet and we retransmit it, the second time it gets retransmitted, as we just seen here, this is the retransmitted or lambda prime in. The second time it goes, there's a free buffer space and eventually goes to the receiver. So at sending low rates, this isn't a big issue for us when it comes to the idea of retransmission. And almost every packet is going to get through. So in the region of A out or lambda out, the receiver throughput still increases linearly with the lambda in. So the slope of the curve is about 1. But as the sending rate increases and approaches the maximum length or the R2, the packets start getting dropped more often. So that means the retransmission is still taking up more space in the network and consuming capacity without increasing the throughput. So the result on the top that you see with the gray and the black is that on the top right of the plot, this is the wasted capacity because of the cause by the retransmitted packets. So even though more data is being sent overall and it is being received, the effective throughput stops increasing. So now expanding more on the scenario. So let's drop the last assumption, meaning that not all transmission are actually needed. And what would happen here is that you send out the data, takes a copy of it, it goes to the buffer, there's free buffer space. And then here what we have is a delay, some sort of delay. And we saw that the timer has ran out or expired too early, so another packet is getting retransmitted. So in the real world, the sender time may expire too early. That is something that is the timer is already set for us. We can't really change it or change the time. But because of delays, the timer would run out and the packet would get retransmitted. So we would send 2 copies of the same packet onto the network because the sender does not know the packet has been delayed. So it retransmits. But the receiver only delivers 1 copy to the application. So it neglects the prime lambda, it just takes the lambda in as an output for the receiver. So these unneeded retransmission now add more total segments into the flow. They also take extra capacity, and some retransmissions are necessary, but others are simply just duplicates. And also they add congestion. Whether we are retransmitting duplicates or congested or delayed packets, they're also adding on to the congestion without helping the throughputs. So in the graph, what we can see here is that we can see the effect. The throughput curve now drops even further. So the wasted capacity from these unnecessary retransmission reduces the maximum available or achievable throughput below R/2. So in this realistic case, congestion causes delay. It also causes loss and now also wasted work. So sending packets that don't increase throughput at all. So we're going to keep building on these scenarios until we reach the ideal solution for this. Yeah, this is just the wasted thing that we have. So I just want to summarize what we've seen in scenario 2. So when congestion happens, packets are lost and needed to be retransmitted. That is extra work for the sender. In many real cases, senders also retransmit unnecessarily, sending duplicates copies that both get delivered. Also, these duplicates also consume link capacity, but we know that only one copy contributes to the actual throughput. So the network ends up doing more work to deliver the same amount of useful data that we have. Each retransmitted packet takes up buffer. It also takes up bandwidth and time. So all this reduces the network efficiency that we have. So the result is that the maximum achievable throughput drops below the physical link capacity. So congestion itself doesn't just cause delay and loss, it also leads to wasted effort and lower overall efficiency in the network. Does that make sense, that what we discussed in scenario 1 and 2 so far? So here's an analogy for scenario 2. Imagine a post office with only a few mailboxes. They have a finite buffer here. When the boxes all get filled up, new mail cannot be placed. So it gets returned to the sender. The sender thinks the letter was lost, so they resend it. Now the office has to handle both the new one and the return or the resent letter. The letter that they originally sent has to be resent back to the original sender, and the sender was like, "Hey, something happened. I want to resend the mail again." So it makes the problem even worse or causes more work for the post office. So the total incoming mail rate keeps rising, even though the delivery rate stays the same. So this is what actually happens in the network. The retransmission adds more load, increasing congestion instead of relieving it. Here in this scenario of 3, we're gonna move on to more than a single router. We're gonna go to more routers, and that is typical when you do usually ping. When you ping Google, your ICMP initial ping is gonna go through multiple routers that are happening, and that is typical. So here we have 4 hosts, so we have 4 senders, and we have multi-paths, and there's also going to be timeouts and retransmission. So first, let us focus on the red flow. So the red flow, or the red line that you see, is going from host A to C. It crosses 2 hops. So just like before, retransmission can happen when packets are lost. Let us just distinguish between the original data and the retransmitted data. We know that lambda n is the original data, and lambda prime n is the retransmission data. We know that retransmission happens because of either delay and the timer runs out, or packet buffer, or the buffer is getting overflow and the packet needs to be retransmitted. We also have other flows that could happen, or other things that can happen. We have the blue that is going from host D to host B. We have another one that is going from host B also to D. We can have another one that was going from host C to A. So let us just focus on the red here, the red link exactly. So one thing to notice about the red link is that it shares one of its links with the blue flow. The blue flow is also using that buffer. So that means for a red packet to reach its destination, it must also successfully forward both routers that we have. And we have here multiple routers, and the idea is gonna be crossing multiple routers. So if it's lost at the second router that we have, here's the second router. If it's lost at the second router, the sender must retransmit, which means it crosses the first router again, doubling the wasted work. So retransmission also adds up. Another way to look at it is that every lost packet at the second hop wastes all the retransmission capacity and buffering used at the first time. So as the lambda n increases for all flows, the arrival rate for each router keeps going up, leading to higher loss rates. And then eventually the first hop traffic dominates and crowds out traffic at the next hop. So what would happen is that we can have something that happens like this. As this continues and we see that one buffer or one hop is dominating the traffic, this could lead to the end-to-end throughput for the multi-hop flows approaches zero, as zero throughput for the blue, because host A is dominating and taking all that crowd for retransmission. So packets keep getting dropped before completing both hops. That is the idea that we have here. So this scenario shows that congestion in multi-hop networks can completely starve certain paths, even if every sender is working properly. So that is also something to keep in mind. We started with scenario one, it's perfect. Scenario two, single routers, and now we're expanding to multiple routers. Here's also another takeaway that I want to highlight in scenario three is that when a packets get dropped midway, maybe at the second router, everything used to get there is completely wasted. So that includes bandwidth, buffering, transmission time, used at all the upstream routers. So since the packet never makes it to the destination, the sender will have to retransmit it again, repeating all the work. So even in multi-hop networks, congestion doesn't just waste link capacity, it wastes the whole network-wide resources along the entire path. And the overall effect here that we have is going to be obviously throughput is getting dropped, the queue fills up, and more network goes toward recovering from failure rather than sending the newer data. So there's not really a progress that is being made here. So let's just wrap up and summarize what we learned from all these scenarios. The first thing that we want to understand is that the throughput can never exceed the link capacity. We have an exact transmission rate, and the throughput cannot exceed that capacity of that link. So once it reaches the maximum rate, sending more traffic does not help. It only leads to delay and loss. The second thing that we have is link utilization approaches 100. Delay increases sharply due to queuing buildup. Third thing is that for packet loss and retransmission that we have, reduce effective throughput since the link carries both original and retransmitted packets. We know that. And fourth, unadded duplicates make it even worse. So since they take up the link capacity but don't add new data. And then finally, we have on multi-hop networks, any packets lost, downstream waste of all upstream transmission. So we are focusing on what is already being sent and trying to retransmit it. And the buffering is used for that more than sending newer data. So all these together kind of highlight the causes or the costs that can happen with congestion control. And they explain delay, loss, inefficiency, and collapse, even if it's uncontrolled. So that's why we are going to transfer to the congestion control mechanisms to prevent the network from having these issues or preventing the network to overload itself, or being overloaded, even the buffers as well. And what we're going to learn for the mechanisms is going to be what is being used in TCP. We're going to learn some approaches, but within these approaches, there's different algorithms or detailed mechanisms that we will cover next week. So approaches to congestion control. So we know why it happened, and we want to see how TCP deals with it. So the first approach that we have is called end-to-end congestion control. And in this specific approach, the network itself, it's better to have all these out. So in this end-to-end approach, this is one approach of solving this issue. The network itself within this approach does not provide explicit feedback about the congestion. So there's nothing really going on with the network. What is being communicated is between the sender and receiver. They have a way of communicating of the congestion that is happening. So the TCP must infer congestion based on solely what it observes. So specifically, the packet loss is taken as a signal of congestion. So when a packet is lost, that is given us a signal of congestion. So if a segment times out, the set time we have for our packet, or if we receive 3 duplicates, acknowledgements are received, TCP already assumes those packets are dropped due to congestion. And when we have these as dropped, this is a signal for us. So when that happens, TCP reduces its sending rate and it shrinks the congestion window size. So some newer TCP variants also look at the increased round time trip, and that can be an early sign of congestion. And longer round time trip means packets are spending more time in queries or in the buffer. So TCP end-to-end approach relies entirely on the sender and its own observation. So there's not direct signals that are coming from the router whatsoever. So let's look how this works, the end-to-end congestion control. So the basic idea behind it, congestion control is simple. So when a sender detects congestion, it reduces its sending rates. So here we have data coming from one host or a sender, and there's acknowledgements that are coming from that. So we use those acknowledgements as a signal for us and to help the congestion control. Here, the routers that we are going through don't have really an explicit say or any useful information that can help us. So instead, TCP infers congestion based on what it observes. And we said that if packets are lost, this is one signal. If time is run out, that is one signal. 3 duplicates acknowledgement is also another signal. Or if the arc of the round time trip increases, TCP assumes the network is being congested. And then if it noticed that, then it would slow down its transmission rate. Typically, it reduces the congestion window that we have. So this approach was part of the original TCP and IP design and remains central to how TCP operates today. And it's efficient because it doesn't require network support. So, but if we think about this approach, it is one approach that we have, but is it the optimal approach? It is slower to react here because since it only depends on indirect signals like delay and loss. So here's an analogy of the congestion control approach that we have. Imagine that you are driving on the highway and there's no really traffic reports, or you're not using Waze or to let you know there's traffic jam, or you're not using Google Maps, whatever these applications that we have. So you have no direct feedback or any source of feedback to let you know what's going on, whether from road sensors or signs. So you're just basically going on your own experience, right? So the idea is that when you see brake lights ahead, you start slowing down. So you infer that there's congestion on your own. So you naturally slow down to avoid hitting other cars. That's your way of reducing the sending rate. So that is the end-to-end approach. Once the road clears, you speed up again. And these signals or indications that we have are the same indications for us to say, hey, we can speed up now. When the round time trip reduces, it becomes to its original time. When there is no packets that are getting dropped, or when there is no 3 acknowledgements are sending back. So this is how TCP behaves. It doesn't get explicit warnings. It just infers congestion on its own based on the sender and receiver. And it takes these into considerations for delays and losses and adjusts accordingly. Here's the second approach that we have, and this is called the network assisted congestion control. So unlike the TCP end-to-end, here we are going to utilize the network itself. So it's going to take a role or participate in detecting and signaling congestions. So the routers themselves are going to provide explicit feedback for us to the sender and receiver about the current congestion states. So this feedback can be as simple as a single bit indicating that congestion has been detected or on a link. We will discuss the details of this approach in the next lecture, but a single bit change here, it could be like bit changing from 1 to 0, 0 to 1. For example, here in the ATM or available bit rate, the ABR, congestion control, the router tells the maximum rate it can safely send. So this is another common technique is packet marking. So when a congestion occurs, the router sets a bit in that packet header and it passes it through. So that is an indication that we have. So the receiver then informs the sender when the data gets received and the buffer or the network takes control or takes a role. The receiver will say, hey, I received that something is different here in the bits. I'll let the sender know. And this is more faster and accurate control rather than end-to-end approach. But it also requires coordination or involvement of the network itself. So meaning the routers and protocols must support these mechanisms that we have. Let us take a look at the network congestion control. We still have the same idea here. We have a buffer. We have different routers and different paths. So data is getting passed through and acknowledgements are getting sent back to the receiver and sender. The router here itself is going to detect congestion and provide direct feedback. And this feedback is going to travel along the same path as the data, either forward or backwards. And we see that we here have the router plays an explicit congestion, provides explicit congestion info, telling the sender or receiver of information like maybe it is busy, or how busy the link is, or what is the sending rate should be. So, for example, protocols like TCP, ECN, ATM, ABR, Despit use this idea to mark or notify congestion control. And these are specific protocols, you can say, or mechanisms that fall under this specific approach. So unlike TCP end-to-end approach, this method only gives back the sender real-time visibility into what's happening inside the network. So it allows it to faster react and more precisely. We don't have to wait on these three indicators. We can use the router and the network itself to provide these info. Human analogy of the network assisted congestion. We're still going to go back to the driving idea, and you're still driving on a busy highway. In this case, the routers are going to act like traffic officers. When you see traffic officers near or lights are on, that means something is going on exactly. And we know that we have to slow down, or we have smart traffic lights. They are now implementing, I think, on our highways that we see, or you have the apps that we use that tells you, hey, the path that you're going, it turns from blue to yellow on Google Maps or red. These are indicators for us that there's going to be jam or delay. So we need to slow down. So this is the idea that we have. So when traffic starts to jam, they're going to send real-time signals like warnings, adjusting speed limits, tell the drivers, the senders to slow down before a full traffic jam happens. So this way congestion is measured collectively, not just by the drivers guessing, but the system actively coordinating. So everyone on the road. So that is where we are so far. So we looked at the causes and cost of congestion, and we explored there's two main approaches to deal with that. And we said there's an end-to-end approach used by TCP and the network assisted approach that provides explicit feedback. With those foundations that we have in place, we are now ready to dive into like deeper of how these exactly work and how TCP actually performs congestion control. So in this section, we only study TCP uses and many of the same ideas we just discussed, especially interference from loss and delay. And then we'll study TCP. We'll study the classic TCP congestion control. What are the advancements? How does the sender gradually increase the sending rate until occurs, happens, and then it goes back off? We'll also explore a delayed-based approach, which measures the round time trip as a sign of congestion. And then we'll finally visit the next idea, the network-assisted idea, network providing explicit info. This is the time that TCP explicit congestion notification, it's a ECN mechanism that we'll explore in the next lecture, where routers help signal congestion before packet loss. So that is what we're going to discuss on next Monday. So that is it for this lecture. I said it is going to be a short lecture compared to the one we had on Monday. And I want to cover fully TCP itself on next Monday and the mechanisms that we have. So that is that. The grades have been out for everything so far except the programming assignments. So that will be released today. And usually if you have a problem with the grade, reach out to the TA that left a mark before coming to me and we can deal with it. Okay? If you have any questions, you can ask them. If not, you're free to go. Yes, Tiago, the TAs can see the comment section of the assignments. They are usually see them and they leave comments there for you guys. So once you get something and it tells you the name of the TA, you are free to reach out to them or visit their office hours to discuss the grade or the deduction that you have gotten. Okay. Thank you, everyone, and I'll see you next Monday, okay?